Alright, in this video we're going to look at one-sided limits. And there are two one-sided limits, the left-hand limit and the right-hand limit. And the left-hand limit's notation, it looks a lot like our regular limit notation. So the limit as x approaches a, we have this f of x. But the one addition here is, for the left side, I'm approaching it from sort of the negative side. I'm less than that. So I'll put a little negative sign up here as like an exponent for the a. And what this means is, in sort of the working definition sense, is as x approaches a from the left, f of x approaches L. And I can also use an epsilon delta method for this. If I'm approaching a from the left, I only take a delta step to the left. I don't take the delta step to both sides. Right-hand limit, similar idea. Limit as the x approaches a, and again, I would have this sort of exponent, but from the right's the positive side, so I'll put a little plus sign up here, as in sort of exponent of the a. It's not an exponent, but that's what it looks like. F of x is equal to L. And in this one, as x approaches a from the right, f of x approaches L. So let's look at a couple of examples, and I'll give a little bit more information on this and how it ties into values of functions and the limit in general of a function in the first example. So given this piecewise function where f of x is equal to 2x when x is less than 1, 4 when x is equal to 1, and x squared when x is greater than 1, I want to evaluate the left-hand limit, the right-hand limit, the value, and the limit. So before I get started, I can look at a graph to see what's going on here. That's one option. So I know that when I am left of 1, I follow the 2x. So at 1, 2x would evaluate out to 2. So let me put this in here. But since this is not included, the point 1, 2 would have an open circle here. And as I go left, it's the line with slope 2. I can put in some more points to see that I go through 0, 0. I go through -1, -2, so forth and so on. At x equals 1, my value is 4, and that's just the point 1, 4. To the right of 1, x squared is, the function is x squared. So again, I would sort of put in the 1, and 1 squared is 1, but I don't include that because that rule is not included, does not include x equals 1, and then I go sort of quadratically. So I'd go through the point 2, 4, I go through the point 3, 9, and so forth and so on, curving upward. So this is what the function looks like. And now I'll use some different colors to show how I get this. So the left-hand limit, first of all, I'm approaching 1 from the left side, and as I approach that from the left side, I'm going to be on the first rule, because this is where we are left of 1. And I can see that I'm approaching the value of 2, so the left-hand limit is equal to 2. From the right side, I'm going to be on this portion because to the right of 1, x is greater than 1. And so as I follow x squared approaching x equals 1, the output y value is also 1. So this limit is 1. Notice for neither of these limits do I care what happened at 1. It's just approaching 1. At evaluating f of 1, this is where I actually care where x equals 1. And when x equals 1, the value is 4, so f of 1 is 4. And let's see, do I have another color? I guess I'll just go with this purple. So for the limit as x approaches 1, the regular limit of f of x as x approaches 1, I consider to the left and to the right. I do not care about what happens at 1. From the left, we are approaching 2. From the right, we are approaching 1. And since they're not approaching the same value, this one does not exist. So graphically, that's how I can solve that. Now, I have another option. I can just sort of consider what's happening over here. So I can try to sort of make a table or construct this. And if I consider points that are left of 1, well, 0 is less than 1. And I'm going to follow this rule, so I could consider, okay, when x is 0, 2 times 0 is 0. But that's pretty far from 1, so I can do better. Let's do 0.9. 2 times 0.9 is 1.8. And what about 0.99? Well, 2 times 0.99 is 1.98. You can see as I'm approaching values for x that are approaching 1 from the left side, less than 1, my outputs are approaching 2. So I didn't even need the graph. I just say, okay, if I'm on the left side, I consider this. From the right, I do the same type of thing, except I'm going to consider values that are bigger than 1. And so I could consider 2. And to the right, I'm going to follow this rule. So I can consider, okay, 2 squared is 4. But 2 is pretty far from 1. I can do better. So I can consider 1.1. And 1.1 squared is going to be 1.21. And I can do even better now. Let me see, can I do this in my head? 1.01 squared. Notice I'm making my x's approach 1 from the right-hand side. And 1.01 squared is going to be, I believe, 1.0201, because we end up having 1.01 plus 0.0101. And you can see these are approaching 1. And the last thing to note is this, and I said I was going to tie this into regular limits. So if the left-hand limit is equal to the right-hand limit, oh, did I put -1? I did. Hold on, sorry, not -1. I keep in mind to put -1 there. Left-hand limit is equal to the right-hand limit, then that will be the overall limit. So the limit as x approaches a of f of x will also equal L. If the left and right-hand limit evaluate to real numbers and they're not equal, then it automatically does not exist. If we only have one side over the real numbers, it's a little bit trickier. In AP Calculus, we're only going to consider real numbers. We're going to sort of ignore problems like the square root of x and asking what the limit of the square root of x is at 0. It does happen to be 0, either if you only consider x's in the domain, or if you allow for the imaginary plane, we're sort of approaching 0i over here. But this stuff, beyond the scope of AP Calculus or a Calc 1 course in most cases. So if they both are real limits, and they approach the same thing, that is the limit. If they both have real limits and they approach something different, then the limit does not exist. One final example. And this leads into a problem that I've seen somewhat often on AP Calculus tests or AP practice material. We're given a piecewise function. I want to find the value of k that allows this limit to exist. In order for this limit to exist, the left-hand side, kx plus 3, and the right-hand side, x squared plus k, must approach the same thing or value at -2. They must be approaching that. This one from the left, because to the left of -2, we're going to consider this function, and this one from the right. And so all I need to do, which we'll get more into later, is say, okay, this is a line, this is a quadratic. This will be approaching k times -2 plus 3 when x is -2. This will be approaching -2 squared plus k from the right. And if I want them to approach the same thing, I just will make them equal to each other. And I'll solve this out. I have -2k plus 3 equals 4 plus k. And then I'm going to solve this, so I will add 2k to both sides and subtract 4. So I get -1 equals 3k. And in here, I'm going to divide both sides by 3, and I get -0, well, I say -1/3 is equal to k. I prefer the fraction than the repeating decimal. Now, this looks all well and good, and say, okay, I just make them equal to each other, put in the -2, because I had a -2 here. If this were a different value, then I'd just consider one of these two. But what's going on? And here is what's going on. I'm going to flip over to a little GeoGebra page. I have this line and this parabola. And as I change k, they're going to move. If you recall, let me flip back over to this. The k on the line just changes the slope. The y-intercept will remain the same. And for the parabola, the k is going to just translate it up and down, change that y-intercept. So let's see. So as I make k bigger, you can see they're moving farther apart from approaching the same thing. But as I make it smaller, they're getting closer and closer together until I get to this point right here, where from the left and from the right, they're both approaching the same value. And you can see if I go too far the other way, they move further apart. So the only value of k that makes them approach the same value is -1/3. If you have any questions, please feel free to comment below. I hope this helped out.